Hello. Hello. Let's start, and let's start with exam because it's the end of the term. So the first exam is taking place in 2 weeks, which is February 26th, right? So the Monday. And it's taking place at 10 o'clock, so like our usual teaching hours, and it's likely going to take place in the basement seminar room where you had Cognitive Neuroscience A with Jana. As previously discussed, there will be 10 questions, and for each question you can get 1 point. That makes 10 points in total, max. And it's the first half of the entire assessment, so the second half will happen after the summer term, again with 10 questions. Now for the first exam, there are 2 dates offered. The first date is set February 26th, 10 o'clock. The other date is April 9th, which, then also at 10 o'clock and likely at the same location. And actually these dates are all on Blackboard, and you have that information actually. Maybe not the time, but the dates are there. So who's planning to take the exam in February? Well, that's the majority. That's good. But it doesn't matter, so there are no bonus points for taking the first exam in February or the second exam in April. So how does it work? So the only what you should keep in mind is that you can only so you cannot basically improve. So if you after the first exam have the feeling you didn't quite well and then you want to come for the second date, that doesn't work. So you either submit your exam on the first date and then that counts, or you don't submit an exam and then it doesn't count. So if you want to have a peek of what questions are being asked or whatever, then you can do that, but then you have to cross everything out and fail this first exam. But I think nobody is planning on doing that. So either come and take the exam or don't come and don't take the exam. With respect to the questions, I've prepared this question and answer pool that is there as a handout. It's also on Blackboard. And 10 questions will be chosen from these questions. And they will cover the entire set of questions, so they will be uniformly distributed over the section. So it will not only focus on the last part or on the first part or something. And to get the full 1 point for a question, you should be as precise as these answers are, maybe better, but definitely not worse. Questions.
Do you have anything to register for the exam?
No, you just have to show up. Any other questions? No. I offer an additional Q&A session on the Friday before the first exam, which is February 25th, 23rd, at 4 p.m. also in the basement seminar room. I will send you an email again with the times and the dates so that you don't get confused, but you can also, of course, listen to the video on YouTube multiple times so that you feel confident when things are going to happen. And yeah, so in this Q&A session, if you have something that you want to clarify with regards to the questions. Actually, this will only be about the questions and the exam, not about general things in the course that you found very interesting and somehow decided to ask on that day shortly before the exam. So it will focus on the exam stuff, and once we're done with questions about the questions, then we're done that day. Yeah, that's as much as I can think of right now with respect to the exams. Anything else about the exams? No. Good. Who has started memorizing stuff? Roughly, okay. Okay, but you, that for those people who want to take the exam, it makes sense to have started a little bit. Otherwise, it will be horrible binge learning, which helps no one. Good. Anything else? Any other questions of more or less general interest? No. You used to be more people, right? Anyway, good. Then let's start with the last session that will not only happen in video form. So the aim today is to talk about two-way ANOVA designs, as we hinted at the end of the last session. And specifically, we will first do a little bit of intro and data organization and stuff and plotting, and then we will talk about the 2x2 additive ANOVA design, and then we'll talk about the same thing with interaction. Good. So to start, let's think again what a factorial experimental design is. So we talked about last time that in a factorial design you have experimental factors, which usually have discrete levels. Specifically, if you talk about multifactorial designs in psychology, it's always with discrete levels. You can also have factors with continuous levels, but that's then usually considered in different scenarios. So here we're talking about factors with discrete levels, and usually you then cross all levels of each factor. So if you want to visualize something, it's always sensible to visualize these designs in terms of these little, I don't know what you want to call them, these little visualizations, where you have one factor, maybe let's call this factor 1, and then you have level 1 of factor 1 and level 2 of factor 1. And so this is a visualization of a 2x2 design. Again with level 1 and level 2 for factor 2. And if you have, so the nomenclature here is that you call such a design a 2x2 design, because this is the first factor, so that's factor 1, and there are 2 levels of it. That's the second factor, and there are 2 levels of it. Of course, you can have designs of higher order if you want, so something like 3 by 4 by 2. That would mean that the first factor has 3 levels, the second factor has 4 levels, and the third factor has again 2 levels. And of course you can come up with 10 times 100 times 2 times 4 times 60 designs, but the most common thing, which you also will encounter in cognitive neuroscience, is actually the 2 by 2 design. Sometimes if you have another group factor, so if you're looking at a 2 by 2 within participant design, and then you look at another between participant factor, for example age or some disease or so, then you might have a 3-way 2 by 2 by 2 design. But as I discussed also last time, it's generally advisable to first of all think about what kind of design you have when you are designing your experiment, and secondly not to design experiments which then turn out to be factorial designs of very many factors, very many levels, and not necessarily all the data acquired for everything. So in general 2 by 2 is a good starting point. So in the concrete application that we are looking at, what we have is this DLPFC volume data set, where we had these experimental factors of age and alcohol intake. And here we can then, if we consider our specific design, we can visualize that as follows. Here we have alcohol here, and then this is low and high according to some threshold that splits the data in half essentially. And then we have age and have young and old. So what are these cells now? The cells are meant to represent the data that you acquire in each of the cells, and it's usually assumed that you acquire data from all of the cells. So that means you have DLPFC data, now concretely DLPFC data from young participants that have low alcohol consumption. You have data from young participants that have high alcohol consumption. You have data from old participants that have low alcohol consumption, and you have data from old participants that have high alcohol consumption. Yeah, so you have in total, if you think in terms of experimental conditions, which here is not really an experimental condition but an experimental setting, but you have as many conditions as you have cells. So if you're designing this, for example, from an fMRI study, you have a 2 by 2 design, then you should be aware that you have you need to have experimental trials for each of the combinations of your levels of your factors, which then is essentially the number that you get by multiplying the number of levels from each factor. So in this case, it would be 4 experimental conditions. Now, what is always helpful with these designs is to adjust the notation of the data according to the designs, and the way I did that here in table 14.9 is essentially by giving the data points 3 subscripts, where I indexes the levels of the first factor, so that's factor 1, with the levels 1 and 2, which are of course low and high alcohol, J with levels 1 and 2, for the second factor, and K for the number of the data point in the respective cell, which then would go 1, 2, 3, up to the number of data points you have in cell ij. So if you sum these 4 nij's over I, which goes from 1 to 2, and j, which goes from 1 to 2, you get the total number of data points. N. So basically what happens is that you write these into your little thingy. You don't, of course, have to do that ever. I'm just trying to visualize this here. So that was alcohol, low, age, young, and now here we would, that depends on how you want to do it. So I find it more, whether you want to call alcohol the first factor or age the first factor, that's essentially up to you. I would feel it's a little bit more natural if we now do a 2 here, because then actually we would change the first factor to be age, because then it's the row factor and it feels a little bit more sensible in terms of how it looks and how we write it up. And here we would have then 1, 2, 1, 1, 2, 2, 2, 1, 2, and 1, 2, and y 2, 2, 1, 2, y 2, 2, 2, 2, 2, 2. Sorry. Sorry. y2, 2, and 2, 2. And 2, 2. Good. Questions about this at this point? No. So these y's with the 3 indices, they are the data points / the random variables that you conceive your data points to be realizations from. Now, if we assume that these are data points, and of course they are also located or written down in the table there, then one can compute, of course, for each cell, one can compute an average, and one can also compute a measure of variability, for example, standard deviation or standard error of the mean, according to the standard formulas. And then one can visualize that, and there are different ways to visualize that. So you might be familiar with these kind of SPSS style plots that look something like this or so. I think one can also do that simpler, just by doing bar graphs, and this is what we have here. So in terms of the experimental conditions, we could, for example, do it like this. This would be young age, low alcohol, young age, high alcohol, old age, low alcohol, old age, high alcohol. Of course, you can think whether you want to plot them like this or like this, but you should at least think about it. So what you see here is in terms of the rotating, or the rotating of the factors. Here that's changes the alcohol. Here that changes the alcohol, and from this to this changes the age. And then you can visualize the averages and some measure of variation simply in bar graphs. So then you see maybe such a pattern, something like this. And then there are always two things, or in terms of 2x2 designs, actually 3 individual things that are of interest, namely main effects and interactions. as we briefly talked about last time. Main effects, so main effects always refer to experimental factors. So if you have 2 experimental factors, you can have 2 main effects. If you have 3 experimental factors, you can have 3 main effects, essentially 1 effect for each experimental factor. And the question is, for main effects, averaged over the levels of the other factor, is there a difference in terms of the levels of the first factor? So if we think about the main effect of maybe H first, then the question is, does H affect the DLPFC volume? In our case, does H affect the DLPFC volume from the information that we have? And from the information that we have, we see that for young, we have 2 kind of data points here: young for low alcohol consumption, young for high alcohol consumption. If we eyeball that, then we would think, okay, roughly on average for young, the DLPFC volume is here. For old, roughly the DLPFC volume is here. Is there, and then the question is there a difference between this and this, between these 2 values? And then without now asking about a difference with respect to the variability, because this is something, of course, you need to into account. But just from looking at it, yeah, it looks like in the young age group, there is more DLPFC, or the DLPFC volume is larger in the young age group compared to the old age group. Yeah. Of course, this is not, doesn't tell you anything about the significance, because for significance you would have to do a test and check whether this holds against the variability. But just from looking at it, you get a fairly good impression whether a main effect of age is there. Same for alcohol. This is from, if you plot it like this, maybe a little bit harder to see, but now you have to think about the low levels of alcohol. So this is a low level of alcohol, this is a low level of alcohol. If you think about their average, then, well, it's roughly here. Then you have a high level of alcohol here and here. If you think about their average, well, it's definitely lower, because this is higher than this and this is higher than this. So again, yeah, it looks like there is a main effect of alcohol. Yeah. Who has seen this before? So main effects and interactions? And you're all clear about it. It's not surprising. Good. Then effect alcohol. Then by looking at the pattern of data here, do you think there's an interaction? And if so, why? Or if not, why not?
And I think there is, because the properties seem to be very equal. Mm-hmm. So the interaction is a difference of difference, right? So I don't see that there.
That's very good. Yeah, exactly. So the interaction, as you said, that's a difference in differences. And sorry. And then according to your design, you can have different numbers and different orders of interactions. So in a 2x2 design, you can only have the interaction of the first factor with the second factor. If you have a 3 factorial design, so a 2x2x2 design, then you can actually look at interactions between each of the factors. So you have the interaction of factor 1 with factor 2, and the interaction of factor 1 with factor 3, and the interaction of factor 2 with factor 3. So that would be 3 interactions that you are potentially interested in, plus the 3-way interaction of all factors. So, and as you said, here it doesn't look like an interaction pattern, because the difference that goes from here to here, for example, if we look at the manipulation or the effect of the alcohol at the fixed level of young age for factor 1, that difference doesn't look much different than the difference here between the levels of the alcohol factor in old age. It would be completely different, of course, if, now we can play a little bit here, if here these two would be identical. So then there would be a difference, also an influence of alcohol for young people, but on the DLPFC value, but not for old people. So there's another potential interaction effect, of course, that that the pattern reverses essentially. So here you would have a very strong difference in the differences, because it would already turn around. So this would be a negative, or depending on which direction you go, this would be a negative effect of high alcohol. And here, for the old people, drinking would really make things better in terms of their DLPFC volume. So what this is supposed to point out is that just stating that there is an interaction is actually not that interesting, because it's more interesting what kind of interaction effect you have. And I think these actually also have names. If you look into psychology statistics books or so, then you can give names to these different kinds of interactions. But what is always helpful is to visualize the data. So if you write a paper and just report there's some interaction and you don't visualize that, and then you don't even interpret what that should mean, then it's completely pointless. DLPFC. So what else about interactions? Visualize them. So this is basically looking at the data and identifying main effects and interactions, and of course not modeling them and also not testing them. Another thing that sometimes comes up in neuroscience, there was also, that people like to write these papers that everybody's doing everything horribly wrong. And you sometimes see that also when people report the results, and it can actually be sometimes more subtle. So sometimes you have the case that people do something like this. They show you, okay, in this case with the young people, we have a significant difference. And here we don't. Something like this. And then they say, that means that in the young people, this makes a difference and not in the old. And there you can always come with the critique that they should test the interaction and not test individually the effect here and effect here. And if they don't find an effect in one of the cases, then you shouldn't formally conclude that there is now that the age factor in this case has some modulatory effect on the alcohol factor for the DLPFC volume. So this can sometimes be more subtle, that people do correlations, and then they find some correlation in simple regression in some condition and not in the other. And then again, they make a story about it, and then again you can say you should test the interaction. And there's a paper in Nature Neuroscience that where some people tell other people that they should do that.
Can you explain why this is not valid? Because after you do the test for interaction, you would test this too, right?
nothing is really valid or not valid. You can do whatever you want. Nobody gets hurt, nobody dies if you do that. So, unless they don't base a concrete treatment based on your results. So what is not valid about this is that if you somehow manage to describe this in terms of an interaction, even though you don't really know what an interaction is, because otherwise you would have tested for it. So you make a big point about this modulation here in the young compared to the old age. But you have not formally made sure that actually this difference in the difference effect is large compared to the variability that you have. Because the idea is, but this is then of course in these papers also not explained in detail. And the idea is that you always have to think in terms of statistical significance. You always have to think in terms of the relation of the mean with respect to some measure of variability. And of course, it could happen that if you test for the difference here with respect to the variability over this, and you test this with respect to the variability over this, then you get high effects of these differences with respect to the variability of these differences. But if you test for the size of the differences in terms of the variability of the differences, then it might not be significant. So you have to think how you compute these statistics, right? So you have to, here you would have to compute the difference between these data points and these data points and the variability of these differences. And here you would have to compute the differences of these data points and these data points and the variability of these differences. Now if you compute the interaction, you would have to compute the difference between this and this and so the difference between this and this minus the difference between this and this. Maybe you get some other variability there. So it's actually not there. So this would lead more thinking, actually, in terms of when this actually will lead to a problem. I'm not saying that this will always lead to a problem. I'm just telling you that other people say that this is a problem. And so it can be that based on these statistics, your interaction effect is also fine. It's an interesting master project, actually. So if you want to do a master project, one can look more into that. Yeah. Good. So much about the intuitive stuff. Any other questions about this? Have you seen 2x2 designs in your papers that you are constantly reading? Good. And have you seen graphs like this? Good. And has everybody always tested formally for the interaction? Good. Good. So that is kind of the intuitive story about 2x2 designs that you also need to know, because otherwise the formal stuff doesn't make much sense. So then we can actually start now writing down the model that or a model, a GLM model that can be used to account for these facts. And we start by looking actually at an additive two-way ANOVA model that doesn't involve an interaction effect. This also shows you something that you can model data in different ways, even if you have a specific design. So second topic then is 2x2 additive ANOVA. So the story, of course, is as in the entire fundamental designs story is always the same. So we are now interested in regarding our data points as realizations of random variables, and we ask what kind of random variables are those. And then, of course, we assume for each of the yi, j, k, where again I is the levels of the first factor. And of course, we can generalize this, that it's not only 1, 2, 1 and 2, but maybe goes on to c, which is the number of maybe let's say r, which is the number of the row factor levels. So think that the first factor has 3 levels, then it would be 1, 2, 3. But you can, if it's easier, you can of course just think 1, 2. J is then the factor of the column. J is the index for the column factor. Maybe it goes up to c. Again, it's in the specific case it's 2, but it could be more. And again, k is the index of the data point in the ij combination, where again, if you sum over all levels of each factor, you get the overall number of data points. So for these random variables, we assume, of course, like always, that they are realizations from a univariate Gaussian with expectation parameter ij and variance parameter sigma square. So what this means here, this mu ij, is of course that for each cell of the designs, for each combination of factor levels, we assume a common expectation. Yeah. So the idea is that if the levels of the two factors are fixed, then we assume that this would roughly give the same data, but of course with some variability. Go away. And of course this is equivalent, like always, with the idea that this random variable, aka this data point, is a realization from the combination of epsilon ij k, which is normally distributed with expectation 0 and variance parameter sigma square. Yeah, this is the standard thing. And then the question is, and that's the crucial question, what is the model for these expectations? And there one can, of course, again do different things. And the first thing that we now consider is a purely additive model, where one conceives the expectation of the ij random variable as the sum of an offset, so kind of a DLPFC baseline in our case, plus the effect of the first factor plus the effect of the second factor, of course always with respect to its level of interest. Yeah. So just for an example, if we have the second level if we have the second level of the row factor and the first level of the column factor, this model would say that we have mu 0 plus alpha 2 plus beta 1. Yeah. And this kind of model, if one casts it into Glm form, would have 5 parameters. So our beta parameter in Glm form would comprise our mu0, our alpha 1, our alpha 2, our beta 1, our beta 2. Now, actually, going from here to here, the assumption is made that C, in fact, is 2, and and R is also 2. Yeah. So if you make this more general, and this is I didn't do that in the handout, you can of course make this more general by saying, for example, this runs from alpha 1 to alpha R, and this runs from beta 1 to beta C. And of course you can also formulate this for higher order designs. So that would mean that you need even more subscripts, right? So you would have yi, j, k, which may be just the levels of the 3 experimental factors, and then you would need another index for the data point in each cell. So here I'm not trying to get a full generality, but to exemplify and make that concrete for the common thing that we are interested in, namely the 2x2 design. So, because otherwise one would really have to write a lot of stuff down. So how does that then look in terms of a Glm formulation? Well, of course, the data needs to be organized in column vector form. So we have to put the data from all cells, one below the other. How do I do it there? We have to be a little bit careful. Let's see whether this actually works. So that's now our data vector. It's our y. And then again with our design matrix and our beta parameter vector, we want to recreate the structural model that I wrote down above. So we want to recreate this. So let's see how we can do that with a design matrix. So definitely we need a column of ones to get our mu0 for everyone. 1, 1, 1, 1, 1, 1, 1. And then we need our alpha 1 for all of the first ones. So we need this. Oops, yeah, no, this we don't need, because this now refers to alpha 2. So there we don't need the alpha 1. So we don't need the alpha 1 for these data points here. So we take a column of zeros here, and then select for these data points, select our alpha 2. And then for the first cell, we need the beta 1. So we need ones here. For the second cell, we don't need the beta 1, so we need zeros here. For this part here, we again need the beta 1. And then again, we don't need it. And finally, we don't need the beta 2, then we need the beta 2, then we don't need the beta 2, and then we need the beta 2. So, now if you think about how you multiply this, so if you in the first cell you select the mu0 plus alpha 1 plus beta 1, and here then you select alpha 1 and beta 2, so mu0, alpha 1 and beta 2, and so on. Yeah. So that's the typical, so if you visualize that, and this is also sometimes what you see, for example, if you work with SPM, these things take kind of a familiar pattern. So the dark should be now ones, so you have ones here, and then you have the rotation. Anyway, you know what I mean. You have this, 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 and this. Beautiful. Yeah, so black, black, white, black, white. Good. This, however, is over-parameterized, so we have to, again, like we did for the one-way ANOVA, we have to set certain levels of factors to 0, because easy way to see that this over-parameterized is that you can add up these two columns, then you get the first column, or you can add up these two columns, then you also get the first column. Alternatively, you can again think, okay, we have 4 averages from which we want to estimate 5 parameters, which also doesn't work. So we have to reduce the parameter space, although this was a natural parameter space to use, and this will then change the interpretation of the parameters, but this is what we're going to do after the break.